Welcome in this session on Amazon Aurora. If you are in this session, I suppose you already using relational databases, or you are managing maybe relational databases. And as a former DBA, I know this is not so easy at all to manage relational databases, but relational databases are still core part of applications today, right? So we need to make them more performant. We need to have it cost efficient, and we know this is a challenge. We know it's no fun to manage databases. That's why we created RDS and Amazon Aurora as well, right? So Amazon Aurora is a purpose-built for the cloud relational database supporting MySQL and Postgres. And with Amazon Aurora, we are going to dive a little deeper today. So we are going to do 3 things today. We are going to see how Amazon Aurora is working under the hood. So a couple of features that are there so you can better use it. We're going to look at what innovations we added lately into Amazon Aurora to make it more manageable, more easy to manage, more performant. And we are going to look at one of those features that we added recently, which is called Amazon Aurora Limitless, a way of doing sharding for relational databases. My name is Ovidiu. I'm a solution architect working with AWS and working with enterprise customers, and I'm joined today by my colleague.
Hi, my name is Katja. I'm a database specialist solutions architect. Let's get started. So we at AWS are a customer-obsessed company. Customer-obsessed means that we invent on behalf of our customers. So in the area of databases, it actually started with RDS. RDS is a service that takes care of that heavy lifting when it comes to databases. Something like backups, automating them, patching, and automating deployment as well. Those are things that are going to be taken care of by RDS for you. Second step was then for us to build the first cloud-native database, which is Amazon Aurora. Aurora now decouples the compute and the storage layer, and it allows you to distribute it as well and makes it a very reliable service as it is distributed across multiple availability zones. The next invention was then Aurora Serverless, where you now can scale up and down your compute layer in milliseconds. Allows you to no longer need to provision for a peak, but just use this service and concentrate on what makes your business different. So in summarizing all of that, RDS taking care of that heavy lifting, Aurora one step further, decoupling compute and storage, and then serverless now also scaling up and down that compute layer based on the workload demand. I mentioned that Aurora is cloud native. Now let's perhaps first start with talking about what it means to be cloud native. So it is a service that has been built in the cloud for the cloud, made to harness the full potential of cloud computing. We have a lot of benefits on this slide, and I'm actually not going to focus on all of them because that would take up pretty much all of this session. So we're going to only focus on those that I or Ovi will also dive into throughout the session for you today. First would be performance and scalability. Actually, when it comes to Postgres or MySQL, Aurora shows 5 times the performance, the throughput, of standard MySQL and 3 times the performance or the throughput of standard Postgres. When it comes to availability and durability, actually you're only paying for 1 copy of your data, but we are going to store 6 of those across 3 availability zones. It is, of course, as any other service, always our highest priority to focus on security. So with Aurora, also we encrypt your data in transit and at rest. And all of this is a fully managed service for you, so it comes out of the box, and you benefit from all of these features that the service team has built over the last years. Now we heard how Aurora, or why Aurora is amazing, and I want to now use the next couple of minutes to explain to you how we actually do it, how the system has been built up, and we're going to start with architecture. So if we now start and look at this picture, we see already what I meant before with cloud native. We see that Aurora by itself already has a storage layer, which is a big blue box you see on the screen, and it is distributed across 3 availability zones by default. Then you see those brown orange boxes, depends on what color your eyes prefer seeing. Those are storage servers, and you see 9 here, but of course if you have a system in production, those are going to be many, many more. Now we have this reader-writer instance. This is something you get by default when you start up an Aurora cluster. And then now we are writing actually log records. We're not writing blocks. And when we write log records, we write your data to the 3 different availability zones 6 times. And we actually wait for a quorum of 4 of those 6 to come back for us to acknowledge that write. It looks a little different when we read data, as we keep track of those sequence numbers. So we go to a block that is closest to you and also up to date, which also contributes back to that performance, which I mentioned before. Now, when a storage server fails, since we do peer-to-peer work, we can replicate to a new system without you noticing it, since we do that detect and repair automatically. Same when a storage node fails, so those small little boxes here, those are actually 10 gigabytes each. If one of those fails, because of that peer-to-peer communication replication, we actually repair that automatically. Now, let's build out that storage cluster a little bit, right? So we are adding a read-only node. And as you see here, we are only attaching a new instance to that volume, which means that you don't have to completely copy your data again or create a new storage layer, because we're attaching it to the existing one. Now, of course, additionally to what we saw before, we now also asynchronously do those invalidations and updates to keep the data in sync across those multiple instances. We, of course, also scale out and scale down your system as needed. So if you have a database today, and it is 5 terabytes in size, and you do some work, and then it grows up to 10 terabytes, a week later, a month later, you delete some data, which would mean that it's half the size. We actually scale it back down to those 5 terabytes again. So you only scale for what you're actually using. Now let's talk about one of those things that might happen, right? What if an availability zone fails? This would normally mean for your application, so focus on the application here, and availability zone 3, would normally mean that that application now would go to Route 53, try to get that new DNS record that takes around 20 to 30 seconds for the propagation to take place, to then connect to the reader-writer, the new reader-writer instance. What we now did to help you with that is to build a new plugin, or to improve it. So now with the JDBC driver, you are actually able, because it is aware of the cluster topology, to connect much quicker to that new instance, which reduces your failover time by 66%, which means that would be around 7 to 10 seconds. Okay, so far so good. Let's say we have now one setup of Aurora, it's working in one region, but you have a global workload. You need to operate out of multiple regions. Normally, that would mean that you need to put in the work to actually copy that data to a different region, but that actually is a lot of work, which is why we built Amazon Aurora Global Database. Let's look at this. So we have region A. It's a very similar setup to what we saw before. And what we now do is we add or just enable that second region, secondary database cluster. This means that now you get those replication servers and those replication agents, and those are going to replicate the data over to the second region for you. We actually have a service level objective of doing this, of replicating your data in under 1 second. Now let's look what happens when a write comes in to your reader-writer instance. It gets distributed or sent out to all the normal places, and also to the replication server, which will then send that over to the replication agent, and finally also to the storage layer. Which means that you're now good from a disaster recovery perspective, because your data is synced across those regions. But we now also want to build out that second region, And now you see we have a different, in region B we also have read-only instances. And what we now also do is storage to storage work. So if something fails, we can work very efficiently on the storage layer. We also added a few other features that I won't be able to dive into today, which are things like failing over, switch over, something doing this on purpose. A customer of ours, for example, does this to follow the sun. So they have a global workload, 3 different regions where the time zone doesn't really overlap. And in order to have the latency as short as possible for their customers, they always switch over to the region that is currently active and have that reader instance in that region. Reader-writer instance. A third thing is write forwarding as well. So if you have an application in that B region, you can use write forwarding, enabling this on those reader-only nodes. And then it's going to be sent over to the primary region, to the read-writer instance. And that is then going to use or treat this as a normal write coming from just another client. We now saw a lot of benefits already. We saw how we're building up the storage layer. We saw how the read instances work. But now, also with global databases, we actually want to dive into why this is possible. And the reason that this is possible is the way that we build up those storage internals. Actually, when you look at this from the data block perspective, it is going to look like a standard Postgres or MySQL block. The difference here is the way that we build that storage node. So that's what I want to walk you through now. You have the Aurora reader-writer instance, and we have a change coming in. It's going to the incoming queue first. It's not going to be acknowledged here, as it's not durably stored. Then it's going to be forwarded to the hot log. It's durable now, so we acknowledge that right. Let's look at the second change. Change C is coming in. Same procedure, it ends up in the hot log. We notice as we keep track of those sequence numbers that we are missing a change. So we're using that peer-to-peer gossip to get that change from the other node. And then as we have the complete sequence, we then move it to the update queue and then coalesce it and merge it in storage. This also allows us to, in an efficient way, keep track and also back up those logs and the data, as we don't have to go through the head node. This also allows us to now go another step further. So you see, like, we're building features upon features to use fast clones. Let's start with a use case. So if, for example, you have a reporting application, and your reporting application needs to do some temporary work, and it needs a bunch of new indexes. What you could normally do is use a snapshot from your database, create a new database from that, do the temporary work, shut it back down. But imagine your database is 10 terabytes in size. That's a lot of work, and that's a lot of time and effort to make this happen. What you can do instead is using fast clones. So what you do now, you have an additional layer, which is the storage, clone storage, and you have the clone reader-writer instance. Now you see that we have a lot of pointers from the clone storage to the primary storage. And then when we look at the reader-writer clone instance, it's pointing back to clone storage. If we now read, we actually only read out that pointer, and we're going to read from that primary storage. It's going to look a little bit different when we write to that storage, as that is going to trigger a copy on write. So now we're copying over the data from the primary storage layer, and we're adding the changes that we were about to do. If we now do changes on just the clone storage, which is unshared and not coupled to the primary one, those are just going to pop up. Same if we do changes on the primary storage, which are unshared, we're going to write those log records as well. And then another copy and write will be triggered if we now write to the primary storage, doing a change there, which means that we again trigger that copy and write to that new clone storage. The difference from a cost perspective here, instead of paying for this whole 10 terabyte of database, is that you're now going to write for those blocks that have been changed. We now talked about how you build up your Aurora cluster. You have a huge Aurora cluster, you have a lot of clones, you can have multiple of those. You have a lot of read instances, and you have perhaps also global setup. We now want to dive into how you actually can leverage the data you have in your cluster, how to make use of it for your use cases of today or for your use cases of tomorrow. You might have heard of generative AI. We now want to dive into what retrieval augmented generation is and how you can have this as one of your use cases to benefit from the data in Aurora. Retrieval augmented generation is something you might use if, for example, you get a prompt from the user asking for the vacation days based on their job code in your company and the hours they work per week. That's something that out of the box, the large language model won't be able to answer since it's very company specific. So what you do now is you use a vector store to fetch context, like in this case, the policy documents you have in your company on vacation policies, and then add that context back to the prompt to then ask the large language model on it. How do you do it? You use embeddings. And those embeddings allow you to have a numerical representation of the question the user asked, and also a numerical representation of the context and all the documents you have stored in your document store. This is actually looking similar to this. And with this slide, I only want to focus on the image you see. So you see we have two cities, New York and Paris. And those are, by the embeddings models, turned into some numbers, into a vector. And those values are actually very close together. Same when we look at the below two examples, animal and horse. Animal and horse are also in the same category. So those are actually very close together. Now, the difference here is between those two, right? Between the cities and the animal, that there is a bigger difference. And that's what we try to do with embedding, is to grasp that semantics and the relationships between those words and represent them in a numerical manner. Now, how does it get back to our database session? So we actually have a extension for Postgres, which is called pgvector. It's supported now for those versions you see on here. And it actually allows you to now store vectors with 16K dimensions, and actually 2K of those can be indexed. So if you have a vector with up to 2K dimensions, those can be indexed. 2 indexing algorithms, 2 ways of searching for them, exact nearest neighbor and approximate nearest neighbor, with approximate nearest neighbor trading some of that recall for performance. You're actually with Postgres, since this is the place where you store all your data, you can now co-locate your data with the embeddings, or you can cross-join the data to then have it in the same place. And we have 3 different ways of calculating distance as well in a product: Euclidean and cosine. Quick example here, you see a blog post on the bottom here. Actually, at the end of the session, there's going to be a QR code up here, and you get all the information, you get the slides, and you also get this blog post and other if you scan the QR code. So please, you can make a picture and type it, but you don't need to. So the example here is we're creating a table with a new data type of embedding vector. When we create an index, we can now use that new index function, and then your select will look pretty much the same as before. We're now going to switch gears a little bit, because I want to now also focus on something else where we invested a lot of time to optimize the manageability of Aurora Serverless. If you look at Aurora Serverless, and let's start with a use case here again. You have a workload, and your workload might not be very predictable, right? So let's look at the example of Lambda functions. You have a Lambda function which requires a certain amount of CPU and memory of your database. Over time, you have more Lambda functions, which means you need more CPU and more memory, and more Lambda functions. But you, of course, can also have less and less as the workload cools down again. So now, what we actually did with serverless is have a way of scaling in place in milliseconds on a pay-as-you-go model. Let's look how we do this. In milliseconds, is we use buffer pool resizing. So typically, when you have a buffer pool, it's around 75% of RAM for provisioned as well as for serverless. And then over time, your reads come in. Your pool is heating up. What we actually do now is, because we watch a bunch of metrics, is we're now making room on the instance itself. We're extending the memory to then also be able to extend that buffer pool. As then you read more data, more blocks will come in as well. And now, of course, over time, your workload will also cool off. What we then do is we evict those pages and we shrink back down the buffer pool. So with this, I want to now hand over to my colleague Ovi to dive into another aspect on manageability.
Thank you. Great. So we saw so far what improvements we added to our storage, how we make it more performant, more cost efficient. We saw one of the aspects of Aurora serverless, how we make it easy actually for customers to run relational databases on Aurora with serverless. Now, another question that we got also from the customers is, why don't we have blue-green deployment also for databases? But this is a really common scenario for developers, right? You have a new copy of your environment where you deploy your new changes, and then once you do all your testing, everything is ready, you just switch your traffic to the new environment, right? So why don't we have that with databases? And now we implemented that with Amazon Aurora already, and it's available already in general available with MySQL and with Postgres. And what you can do is actually, for an existing cluster, so let's say this is my source cluster here, it has some couple of read-only replicas besides the writer. What I can do, so I can work with API or your favorite SDK, I can create a blue-green deployment for an existing cluster, right? So this will trigger the creation of a exactly identical in size and setup deployment, which we call it now the green deployment. You can see it also in the AWS console. And then this is, like I said, it's working with MySQL and also for Postgres already. What I can do now on the green cluster, I can start doing some changes, right? So exactly like in software development, I can look and say, hey, I need to do a major or a minor upgrade. So I can upgrade only my green replica independently of the blue one and see if it's working, right? So it's production data, it's just a copy of them, or I can do some schema changes, right? So one of the use cases that I have with my customers was, how do I enable partitioning on a table, right? So enable partition on a table in production, it's a pain because it will lock the whole table, right, for the partition redefinition. And you can do that actually in the green cluster, right, in parallel, wait for it until it's done. And one thing that we also do, once you have your changes, you will always have in parallel from our side the replication of the changes that are happening in the blue cluster. So we try to keep the green cluster in sync with the changes that are coming from the blue cluster. And once you're ready and you have the changes implemented, you can start the switchover. Right? In the switchover process, it's also a managed process from our side, where we stop first all the transactions that are incoming to the blue cluster, the current production, and then we wait until the replication catches up on the green cluster. Once that is done, then we switch over to the green cluster, and we move the DNS as well to the new cluster. So all new connections that are incoming is going to go to the new primary, and then afterwards, if you want, you can just delete your older cluster, and you are ready to go with the new changes on the new primary. Great. This really makes whole life easier actually for our developer, and going forward, making things complicated more easy for our customers. You may heard about, we introduced a zero ETL imperative, so we want to have a zero overhead ETL pipeline between our data services, and we added that between Amazon Aurora and Redshift. So think about the scenario where you have data in your transactional database, and you just wanna replicate what is happening in this database. So, for instance, in Amazon Aurora, to a Redshift cluster just to do some analytics, right? And to do that, currently, I mean, you can build up a data pipeline and you stream the changes. Maybe you put them somewhere in S3 and you do some transformation and other stuff. And this takes time afterwards. It's some overhead, right? And big respect for all the data engineers out there which are doing this. But imagine if you just need your data as it is. Just move it from transactional database, just move it to a data warehouse where I can just run some analytics on top of that, right? So this is where we said, hey, let's do the zero ETL integration. So this is a way of streaming your data from Amazon Aurora directly to the Redshift cluster without doing complex transformations. So that's the use case. And what we are doing behind the scenes is we create that integration targets to the Amazon Redshift, and then we do two steps. So first we seed the existing data, so we copy the existing data from Amazon Aurora to Redshift, so we do that automatically, and then we start a continuous replication between the Aurora and the Redshift. And even if there are different engines at the end, so different database engines, we do that at the storage layer. Right, so, and you can see maybe in the console how fast it is, if it's lagging behind, or if the replication is maybe it's ended with fail. So you can have all the visibility on what is happening behind the scenes. But we take care of that actually for you, so you can have it that replication and get your data insights as fast as possible from the incoming data. Great. Manageability is one part of it, right? So, but we are pushing boundaries also on efficiency, right? So how can we improve our relational database service, our Amazon Aurora, and the efficiency part? And one of the areas that we added, one of the features that we added lately is a new storage type. And just to understand why we added a new storage type to Amazon Aurora, the way we are doing billing today with the Aurora standard is when you have an application, for instance, and it connects to the writer, and you do a request. So until now, you're already paying for the instance itself, right, and for the amount of storage that is stored in your cluster. Now, when you do a select, if the data is on the instance, maybe it's in the cache, you don't pay anything, right? Because the I/O is just reading directly from the memory and is returning the value. Now, if the data is not in the cache, you need to go to the storage. So the instance will go to the storage, and then it will read blocks of 8 kilobyte or 16 kilobyte, depending on your database engine. And then you pay like $0.0602 per each block that you read. The same thing happens if you're doing a write, right? So if you're writing to the database, you're always writing to the, you do an IOP. This is maybe a 4 kilobyte record size that we save into the storage. Even if behind the scenes there are like 6 copies, you actually only do 1 IOP. And you will pay for that 4 kilobyte IOP like the same like for the cost read, $0.602, right? And the challenge here is I cannot really measure how many IOPS I will have tomorrow, maybe, right? Because it's maybe I have a dynamic application, which is just having many requests today, maybe tomorrow has more, the day after maybe has less. So the cost is oscillating, and I can't really predict how much IOPS I will have. Now, and I cannot predict actually the cost of my cluster, right? So we introduce a new storage type, which is called Amazon Aurora I/O Optimized. And with that, we are targeting to have a predictable price for all the workloads, right? So you can choose it directly on your cluster creation, or you can edit it afterwards. And the idea behind is you don't pay for IOPS anymore for different instance sizes. but you pay a little bit more for the instance itself and the storage that you allocate. So it will make it predictable. Doesn't matter how many IOPS you are doing, you just pay exactly the same, like for the instance and for the storage type. It's already available for Postgres and for MySQL, also for serverless version 2, and it looks something like this, right? So under standard, we are looking at paying for the compute, for the storage itself, so the terabytes, the gigabytes that you're storing, and the IOPS you pay per use. Now with IO Optimize, you have a little bit more cost on the compute and storage, but the IOPS cost is gone, right? So you have exactly the same cost for the cluster, independently how many IOPS you're doing. Now, at the end, the picture will look something like this, right? You have an instance that you provisioned, and you have your storage, and you don't have any IOPS cost anymore. Great, and we see not only an improvement in the cost of the cluster, but we for this new storage type, we did some optimization behind the scenes in the storage, and in our benchmarking, we see 20-30% better IOPS for the same instance in comparison with the standard edition for the standard storage type of Aurora. And even the database gets bigger, so you have much more storage behind the scenes, you have bigger instances, then you can have up to 40-50% better IOPS for the same size. Great, really exciting about that. And moving forward to Limitless. So we call it Amazon Aurora Limitless Database because we try to scale Amazon Aurora to really scale to any size of data and IOPS. We're thinking Limitless to be a way of doing sharding for relational databases. But sharding is not that easy, right? So sharding introduces some really complex challenges behind the scenes, right? So think about capacity management. If you have only one database, it's no problem. If it's getting hot, I'm just going to do a bigger database, right? But this is limited on top, so you can only add so much resources to a single database. But when you're doing sharding, you're kind of separating your data in different databases that you write and read independently of that. Then capacity management may become more complicated because maybe one shard is getting hot, and you maybe scaling that shard today, and maybe tomorrow some other shard gets hot, right? So you want to scale that shard again. So all this scalability is complicated. At the end, so just customers that just take all their shards and just scale them all out, right? So it's just adding more cost actually to your cluster, making capacity management actually not so easy. Sharding also includes another challenge, which is resharding. So once you initial shard your database, so you separate the data in different buckets in different databases. Now, what happens if one of the shards is just getting bigger, just getting a lot of transactions, right? So it's filled out, it grows up, so you need to do resharding of that shard. And it's not that easy to do it in online mode, right? So that shard maybe needs to be offline. I'm moving data around in different shards. So resharding it's a big challenge also in like doing shard databases. Another one which is really complicated in general to do with a distributed system is consistency. If I'm doing a change in a sharded database, how can I make sure that it's exactly the same all over the shards? Not that easy, right? So if I'm doing, for instance, a select, and I want to read a count about the data that says distributed over multiple shards, how can I make sure this will be consistent? Because maybe the query is sent at different times to different shards. It's really hard to have a consistent result on that. Not to mention backup. If I want backup of my shards, it will start maybe a couple of seconds, will finish maybe a couple of seconds difference. How can I make sure if I do a recovery of that cluster, that will still be consistent across the shards? That's complicated, but we did that. We did that with Amazon Aurora Limitless, right? So we implemented into Amazon Aurora the Limitless Database shard group. So this is a new group that is just living inside the same cluster where you have also readers and writers. And what we have there are two components. The first one are distributed transaction routers. So for instance, every request, every session that is incoming to the cluster, they are coming first to the distributed transaction routers. And these transaction routers will calculate actually based on which query is sent, where do they need to send the request forward. And they send it to the second part, which is the data access shards. So these are the distributed, let's say, readers and writers that work in parallel and read data from different parts of different parts of the data of a table, for instance. Now they return the data partially back to the transaction routers. They fetch back everything and then return to the customers, right? So this is a purely distributed system behind the scenes, and we do that. We did some benchmarking. We see more than 2 million transactions per second which are supported, so this is really scaling. We implemented resharding. So if one shard is getting hot, right, or is getting bigger, then we do online resharding, right? So you don't really see it behind the scenes. We are resharding the data online, and then we have serverless capacity. So you don't need to mention how big are the transaction routers. You don't need to mention how big are the servers or the CPU. Everything is done in a serverless capacity, so it makes really easy for you to use that. And at the end, we have implemented fully consistency. This is really an ACID system there. So if you're doing a change on one table, it will be consistent on all the shards. How do we do that? How do you do it? we achieve that. We're going to see it just in a minute. Looking at the query flow. So how a typical query flow looks into Amazon Aurora Limitless now. The router receives the session, the query for instance. It will just plan, based on metadata, it will do the query plan to send partial queries to different shards in parallel, and then the shards will receive those parts of the queries. They will do the joins, they will do the scans, they will take the data that's important from the storage, and then will send it back to the routers. And the routers, they do the filters and the joins afterwards and send it back to the client, right? But what if we have transactions? And this is about consistency, right? So how can we synchronize and serialize transactions in the distributed systems? So the way we implemented that is with global clocks, right? So every transaction router and every data access shard has a time, a global time, which is synchronized up to microseconds between them. So we can, based on that global time, we can do serialization of transactions, right? So let's take an example here. If I have a transaction which is doing isolation level repeatable read, and if you work with Postgres, you know there are two types of isolation, right? You have repeatable read and read committed. By repeatable read in a transaction, it means once I start my transaction, I will always get the data as it was at my as I started the transaction, right? So if something changes in between, I'm not going to get the new data until I finish my transaction, right? So this is just purely Postgres implementation. So if I'm doing repeatable read, I send a query to the cluster. The router will assign a timestamp to it, right? So this example is like T100, let's say, right? And using the global clocks, everybody will know when this query happened. So sending the query, it has a result. In parallel, I have a different transaction. Let's say it's a transaction 2. This is another request router happening in parallel. It gets another timestamp. This example is T103, for instance. So if I'm selecting something from a table, so this one is like 801 ID, maybe I get one value, 1. If I'm doing the update on the same transaction and I do commit, the time I'm doing the commit, it will be also assigned another timestamp, which is like T100 in this example. So starting T110, this table has a new value. If another transaction is coming afterwards, it will assign like T125, so it's happening after T100, T110. I will get the new value, right? This is the classical read commit value after it was updated in parallel. Now, if I go back to my transaction 1, and I'm doing exactly the select, like on the table that was updated from transaction 2, what do you think I'm going to get? Yeah, so this will go to snapshot T100 like I started, and you will get all the value, right? So this is an example how we do serialization and different isolation levels in Amazon Aurora, and you can use both of the isolation levels now with our Amazon Aurora Limitless, and use it in a consistent system with transactions. So we support read committed, repeatable read. Now it's available for Postgres, and all reads are consistent because they all get assigned a timestamp behind the scenes. The commits on single shards, like one phase commit, if I only change like one row in one shard, they just scale linearly to millions per second. If you have like 2 phase commits, so multiple shards, we always ensure for you consistency and so ACID transaction atomic. Great. So this is really exciting new features that we introduced with Limitless. Is in preview, so you can subscribe to it and use it in your account. And taking a step back, looking at we talk about Amazon Aurora today, right? So this is just one piece of the puzzle as a relational database in a bigger picture, right? So if we take a step back and we look our data foundation, the data that I'm storing, processing, and using now for the use cases for today and maybe for use cases of tomorrow, they are all in different services. And what we are doing and what we are committed to do is actually to continue to improve and continue to do it better and make it more performant, more efficient, actually on all data workflow services. So you can be sure you can have a really good data foundations on AWS using our managed service. And with that, I'd like to thank you for being here today. And with that, thank you and happy Summit.